Okay, it's an immense pleasure to introduce David Favero from University of Alberta, very good mathematician, a basketball player, and a friend of mine for many, many years. David?
Okay, thank you very much to Ludmil and the rest of the organizers for inviting me to speak and for that introduction, which most importantly included that I play basketball. So, and if I were in Miami, I would have wanted to play basketball with Ludmil this week, but unfortunately, times have changed. So let me instead talk about math. So I want to start with the following setup. G is a, sorry, trying to make the pen finer. There we go. Okay, so G is a linearly reductive group. And X is some kind of algebraic variety. Not necessarily smooth or even irreducible with G action. And L is a G equivariant line bundle on X. Then there's an old definition in Mumford that you can define the semi-stable points of X is the set X and X such that f of X is not 0 for some natural number n, and f is a function of the L tensor power, the G equivariant section of the L tensor power of this line bundle. Sorry, G invariant section. Okay, and so this is part one of this definition. B GIT quotient will vary slightly from Mumford's definition. So I'll say stack in parentheses here. It's just going to be the quotient of this open set by the group G as a stack. And this is roughly, say, if X were projective, this is roughly just Praj of, so I should put the word ample here. Ample, L is ample, so that this is, if I wanted to get X, I'd take Praj of this line bundle. If I want to get X mod G, I want to add this G. The invariant section. Okay. I have more space, but. And then observation. Would be if I have two line bundles, L1 and L2, two ample line bundles. Oh, and I want notation for this, sorry. This is X mod L G. Then since both, I get two semi-stable loci, sorry, I get different two GIT quotients, and they're birational. Since they're both open substacks of, both are open in X by G. Okay. Right. So by the way, I have the chat open on another computer. If there's questions, I should be able to glance over there and see them in the chat from time to time. Okay, so then there's a converse due to Thaddeus, who attributes it to Reed, due to Reed, or in a paper of Thaddeus. So, if X are birational and proper, then there exists some variety Z with a C star action and line bundles, C star equivariant line bundles, such that X is okay. So I guess the takeaway that birational geometry, at least for, say, smooth proper varieties, is roughly varying, which is called VGIT, variation of geometric invariant theory quotients. Okay. So let me do an example. I believe just that X and Y are, I'll say, smooth and proper. So this is a question in the chat. What are the assumptions on X and Y? I wrote proper. Perhaps smooth is an assumption as well, or some form of smoothness. Okay, so example. So X is going to be spec R, X is going to be affine, and G is going to be C star, or GM if you prefer. Okay. And then 1. So this is example 1, sorry. So then this just means that R is a Z-graded ring. The C star action amounts to a Z grading. We can look at the ideal generated by positive elements. Or the ideal generated by negative elements. Okay. And then if we denote by OX of 1, then this is the trivial line bundle, which is ample since I'm on an affine, with twist positive, with non-trivial equivariant structure. So we've taken the natural equivariant structure on the trivial line bundle and we've twisted it by the character corresponding to the identity for C star. That's what that means. Then, so that's a G equivariant structure on an apple line bundle. So this is a C star equivariant bundle. So we can form the GIT quotient. And this is just X minus the 0 set of this ideal, positive ideal. Or this would work for any positive value. You'll get the same thing. For any negative value, you'll delete this negative ideal. And then so sub-example is that if X is spec K adjoin X1 through Xn, Y1 through Yn, these all have weight 1, these all have weight -1, star weights. And this is called diateaflop locally. Sub-example would be if I take the same thing, but I take the singular space defined by this singular hypersurface. So I take the 0 set of this equation. This is called the Mukai flop. Okay. So move on to a more complicated example. 2 is that X is going to be Hom dW. So by this I mean spec sim dW dual. And G is going to be GLV. And L is going to be OX of the determinant. And then X semi-stable is going to be injective maps from V to W. So I'm going to assume dimension of V is K less than or equal to N. Dimension of W is N. And actually, I'm going to put N minus K to be safe. Okay. So it's not needed, strictly speaking, here, but it will be needed at some point for some statement I make. Okay, so right. So then X mod L G is nothing but the Grassmannian KN planes. And you can do a generalization. Generalization. I'll start on a new page. Generalizations. So X is Hom VW cross Hom W prime V. X mod OX determinant. G is the G equivariant bundle W prime V on GER Kn on the Grassmannian, and I took the negative power of the determinant. This is the same bundle Ham WV on Ger Kn prime, where n prime is the dimension of W prime. Okay, so this gives you some kind of flip between these two bundles over Grassmannians. And B, if we consider the zero set, so if B is W is going to equal W prime, and we set X to be the zero set of the composition function, yeah, we want the composition to be zero. So that's a bunch of functions, right? It's k-squared functions. Okay. And this is called the stratified Mukai plot. And or maybe famously it was showed by so the fiber product, so giving you a heads up on where I'm going, then the fiber product does not give a derived equivalence. Okay. That was due to Namikawa. But they are derived equivalent. And that was due to Kawamata for GER2N, and in general due to coitus. Sorry. Okay.
David, the bottom of your page is not visible.
It's not visible? Okay. Okay, so I'll just show it briefly and then I'll avoid using it in the future. Thank you. So I was just saying that, I was just remarking that this Mukai flop is an interesting example from the perspective of derived categories. Okay. Okay. So my goal is related to an old theorem. Well, let's say goals. One, redescribe the GIT quotients using partial compactifications of group actions. Two is obtain comparisons between derived categories of GIT quotients or birational varieties. So I'll, rather than give you all the details, I'll say that this is partially because there was due to an older theorem of Matthew Ballard, myself, and Ludmil. And I won't say it in complete generality, but one. So I'm going to say for nice GIT quotients, and by nice, I'll say like 1, but not 2, in terms of my previous examples, okay? Then I'll say you can compare the derived categories of the two GIT quotients. And by compare, I mean you can either give an explicit semi-orthogonal decomposition relating the two, or in the best case scenario, the two categories are equivalent. So in kind of flop-like scenarios. All right. Okay.
And in what sense case 1 is better than case 2?
Well,
sorry,
I
David.
want to say that it's. I want to say that it's not, but only maybe nice is a bad word. So for certain, maybe maybe this is better. Adjective.
Sorry, David, given that we can't access your previous pages, could you remind us what are the examples 1 and 2?
Yeah, so 1 was a C star action. So let me go back for a second. So 1 was this C star action.
Yeah.
This thing. And 2 was stuff like the Mukai flop, or this kind of stuff on Grassmannians, kind of flopping between bundles on Grassmannians. This is 2.
Uh-huh.
Thank you.
Thanks.
Yeah. So stratified Mukai, sorry. 1 was still the usual Mukai flop and the Atiyah flop. 2 was stratified Mukai for these Grassmannians. Okay. Okay. So I want some sort of kind of universal perspective on this. So the perspective and I should have also mentioned there was independent work by Helper and Leisner here. Okay. So the perspective is going to be GIT via groupoid compactifications. So we want to reimagine GIT stability by thinking about if I have a space G, sorry, if I have a group G acting on a space X. So this corresponds to the action groupoid, G cross X, mapped by 2 maps to X, called P and S. B of GX is X, and S of GX is the action. A little x. Okay. Right. So we want to partially compactify this action. So we want to create a diagram. This is an open immersion, which I'll call J, into some partial compactification Q. some space Q. And we have the action and projection maps down to X. And I want to extend these to Q. Okay. Then I can define, furthermore, you want the boundary, which is, you can define the boundary to be Q minus this open set. Then you want that if you apply the action to the boundary, this is the unstable points. Okay. So let me convince you that this is possible. So I'll start backwards with example 2. So G cross X is GLV cross HOM VW. So I'll write it this way, GLV cross HOM VW. I'm going to compactify, I'm just going to compactify GLV. So I'm just going to take NV cross VW. And then this map took a matrix A comma B. There was 2 maps. I could send it to B, or I could send it to BA, I guess, the way I've written things. And I can do the same thing here. So I have this naturally extends. Right. This was P, this was S, but the same definition works for P tilde and S tilde. Okay, but then if I look at, so the boundary, is just lower rank matrices, non-invertible matrices, cross HOM VW. And if I multiply those by any matrix, I get that the image of the boundary is just lower rank matrices. And now I'm out of space. So, but the point is that that was exactly the unstable locus, okay? So this gives you the Grassmannian, this kind of compactification of the groupoid. Then go back to, I'll say that.
David,
Yeah.
and is the canonical choice of such compactification?
I want to say, I'm going to say the answer is no. And I'm going to explain some scenarios where I have some different choices. Okay, so I'm going to get different GIT quotients by making different choices. Okay, so now I'm going to go back to example 1. And I'll mention that I also talked about the Mukai flop, the stratified Mukai flop, and some other kind of bundles over Grassmannians. For those examples, which was called the Grassmann flop by Donovan and Siegel, for those examples as well, there's some kind of compactification, which I'm not going to describe, at least at the moment, unless there's time at the end. Okay, but so I want to go back to this other example, which was R was a Z-graded ring. Then you can look at the coaction and co-projection. So I'm just going to the category of rings instead of the category of schemes. Looking at these two maps. Then I'm going to define Q is something through which this factors. So here's two choices already. Q could be, you take R join U, and you take the image of the action map. So you take the subring generated by that, or Q could be, you could take R join U inverse. Okay. All right. But I guess in response actually to Sasha's question, I want to say that you can generate the compactification of the groupoid from the compactification of the group. So these are different compactifications of C star. I'm closing up the point at 0 or the point at infinity. And then I'm generating these Q from those compactifications.
And in this case, Q is always
Sorry, I didn't. Can you repeat that?
Oh, I mean, in your previous example, Q was.
Oh yeah,
the
Q is a
product
ring,
of a
right? Yeah.
compactification, and case.
So I'm yeah. So are you upset that this is a ring, not spec Q?
No. I'm asking whether it is whether it always splits as a product. Whether the compactification you consider is always a product of a compactification of G with X.
Okay. So there is an isomorphism with the product, but it's not being extended as a product in this example. So you're not just extending the group action to like a monoidal action on the space. It's mixed. The extensions P total and S tilde are not producted from extending the group action. In the previous example they were, but in this example they are not.
Okay, thanks.
So it's kind of like there's an inconsequential isomorphism with the product. Okay, so then in this example, X mod OX of 1 C star for this, if I call this Q plus and this Q minus, and this corresponds to Q plus. This comes from taking away the boundary of Q plus, and the other GIT quotient came from taking away the boundary of Q minus.
Sorry, David, could you very quickly repeat again what is S hash of R?
Oh, sorry, it's just the co-action map. So it's just the action map. The hash is Hartshorne's hash.
Yeah. You're extending, you're compactifying C star to an A1 basically.
Yeah, this corresponds to, X cross C star. Here, let me just draw the diagram.
Yeah. No, I understand now.
Okay. But just for everybody's sake, I'll just say here you had X cross C star and a map to Q. Two maps. Right. So this is the ring version. That's all. Okay. Thank you.
Mm-hmm.
Okay, and now I'm going to go to an example 0. So there was no example 0. So it's a new example, but I'm going to do X is spec R And for simplicity, I'll let G be C star to the N. So that G equivariant structures. So for example, any toric variety works this way. Well, up to a finite group. On OX correspond to characters G. Okay. Denote by G hat. Okay. So then I can put an equivalence relationship. Chi1, two characters are equivalent if and only if x at mod O of chi1 G equals x mod O of chi2 G. They give the same GIT quotient. There's an old theorem, der Hazare. The stratification of G hat Q by equivalence classes forms a fan. Okay, so now you can look at this GIT fan. You can look at any cone in this GIT fan. Okay. Then if I intersect the cone with the characters, this gives me a submonoid of G hat, the character group, which gives you a map of rings and this is a so this the map of schemes is a partial compactification of G. Okay. So now to this thing, I can do the same thing. I can look at, I have R mapping by S sharp and P sharp to R join G. And I have two maps, which are really just S, the restriction of S sharp and G sharp, going to Q, which I'm going to define to be R adjoin this monoid, which is this submonoid, and the image of the action. Okay. So this would be a product like in the other example, if this image of the action didn't contribute anything. Okay. But in general, it does. And so this is a subring. Okay. Then the proposition due to Ballard, Deemer, and myself was that if you look at take any L in C, right? So take any chi, the way I set this up, chi character in C, then the GIT quotient, well then the semi-stable locus with respect to that character is equal to the complement of this, the image of the boundary for this. Okay, so going back to Sasha's question, he asked me, is there a canonical choice? And now I'm saying, actually, if you look at the entire GIT fan, even not the chambers, just any GIT quotient in this setup, there exists some choice which exactly gives you the semi-stable locus. So I'm telling you what the choice is. So you can reproduce any GIT quotient in this setup, and it corresponds to exactly the monoid you get by looking at a cone in this thing. Okay, so consequence. So am I supposed to talk for 50 minutes or an hour? Is there an answer to that?
We have you slated for an hour.
Okay. So
Probably Ludmila is playing basketball.
okay.
I'm here 1 hour. Sorry.
Okay.
1 hour.
Okay. Okay, thank you. Okay, so I have 20 minutes. So consequence. So first consider, I'm gonna let Q naught be Q restricted to, well, the fiber product of Q over X semi-stable cross X. Okay. And I'll say this has a G by G action, in fact.
What do you mean? You mean it sits in the P pre-image of semi-stable locus or in S pre-image?
Yeah, it's the P pre-image. So, so yeah, there's a diagram like this. Okay. So you get this, you get a Fourier-Mukai transform, which gives you a functor from the GIT quotient to the stack. Okay. And
Sorry, David. Can I just appreciate the point of this? If I understand right, this is the kernel which is this is the embedding which is constructed with quite some difficulty in Halpern-Meissner theory and in your paper. And is the point that you're somehow, after compactifying the group, you get it much simpler?
yeah, somehow the point's going to be that yes, one, this is the kernel for those papers. Two, this has generalizations. And also that this Q is some kind of functor, and I can therefore use it to pass to derived algebraic geometry and derive it in a different sense.
I see. Thanks.
So can one understand this as a kind of geometric version of a window subcategory?
Yes.
Yeah.
But in general, yes, let's say that the window is the image of this functor. But I'll state what's known, okay? So first of all, let me make an obvious observation, is that if I look at I star composed with phi q naught, this is phi q, and I'm going to write restrict to X semi-stable cross X semi-stable. And the way that Q was set up, this is
What
actually
is I? David, what is
uh,
I?
I is this math is the inclusion. So thank you. Yeah. So I'm just saying I have this functor phi q naught, and I can just restrict. Right? So this is set up, I'll say that, so that this is the equivariant diagonal. So this is the identity map. Okay, if I go back, for example, in this case, when I localize away from this cone, when I invert the other elements in the negative of this cone, for example, I'm going to see that I get this entire thing, RG hat, which is the equivariant diagonal. Okay, so if you just convolve these Fourier-Mukai functors, you'll get the equivariant diagonal.
David, I don't quite see. I guess the equivalent diagonal is just x times g. Isn't it the case?
Yes. Yes.
But you say it is q.
No. When after restricting, right? So Q.
Okay. Sorry. Yeah, sorry.
After I compose with the pullback. So after I restrict Q, I'm just saying that Q is the diagonal off of the semi-stable locus. Okay.
No, I mean, still there is something wrong. So it seems to me you consider phi as a functor from XSS to X mod G, right? Then the composition, no.
This is on XSS.
Sorry,
Right?
sorry, everything is fine.
Okay.
Yeah, sorry.
Okay. Okay. So this implies this phi q naught is always faithful. But in general, we didn't know when this was full. So the question is, when is this full? And so at least in the C star case, we got a complete answer to this. But you had to do something extra. So I'll start listing some theorems in the remaining 10 minutes here. So one theorem, this is Ballard, Emer, myself, is that if R is smooth ring with C star action, then A phi q naught is fully faithful. B, the image coincides with window subcategories in Ballard, Favero, Katzerkoff, and Halpern-Leisner. And so I think I'll skip the definition of that. And so C is that.
Sorry, but the window subcategory, I mean, that
do you want me
involved the
to
choice
define
of.
it?
No. I remember those papers, but that involved the choice of parameter. So where?
Yeah, it's a specific one. So so you could call it a canonical one. It's the 1, 0. It's the window W 0 minus that ends in 0.
Mm-hmm. Sure.
Is that okay?
Mm-hmm. Thanks.
So of course you could twist Q and then you get the other ones. And then the corollary is the same comparisons between derived categories. As in, there's one R in corollary and two L's. Okay. So 2 is that this is a theorem. So sorry, let me set it up first. So now if I'll start with I'll say GLV is acting on Hom. So this corresponds to my previous 2. But as you pointed out, you can't go backwards. Okay. So if I look at this GLV action on this space, then the theorem due to Ballard Cheatham-Barham, myself, McFadden, Vandermolen, was that A, phi q naught is fully faithful. I haven't entirely told you what q naught is in this case, but it's constructed similarly, just using the compactification of GLV by NV. Yeah. B is if dimension W equals dimension W prime, phi q naught, well, induces an equivalence. C is that in general, you get an explicit description in terms of the orthogonal in terms of Young diagram on the unstable locus. And D is that the image of phi q naught is given by vector bundles, is generated by vector bundles corresponding to Young diagrams of size k by n minus k for one GIT quotient and k by n prime minus k for the other. Okay, and so for example, if you set W prime equal to the empty set, then you get.
You cannot. Double prime should be a vector space. It cannot be empty space, empty set, right?
Oh, sorry. So yes, maybe 0. Thank you. then you get,
By the way, David, I'm sorry. In the definition of your action of GLV,
uh-huh.
so it acts on a product. Don't you invert your matrix to act on one of the vectors?
Don't I invert my matrix?
From GLV to act on one of the vectors. I mean, you
Yeah.
need to.
Yes, you do. So,
And if you do, then how can you compactify by endomorphisms?
yeah. So I didn't tell you what it was. So I can tell you what it is, but let me finish what I'm saying, and then
Okay, sure.
I'll tell you what it is. So it's similar to how I constructed Q in the other examples. It's not a product once again. Okay, so then you get Kapranov, but in this case, when W prime is 0, there's no negative action. It's exactly just the compactification by NV, and then you just get Kapranov's exceptional collection. So that you're just embedding in the stack by thinking of it as modules over that non-commutative ring, right? Endomorphisms of that exceptional collection. Okay. So I'm going to run out of time, but I'll say quickly that, so if I look at coordinates A and B, this is a n by k matrix and a what is it? Let's say n by k. What did I say? K prime, k by n prime, maybe. Then the Q is k adjoin A, B, C. But what do I want to say? But the maps are as follows. Maybe it's actually better to just say it in this way, I think. You can map from HOM WV cross HOM V. Am I mixing it up now? VW cross HOM W prime V. Now you can still map to, and sorry, I have GLV. You can still map to NV cross this whole thing. It still happens to look like a product, but the maps are slightly different. So you can take, let's say, CAB, and then you can map it to it's actually two maps. So I want to get, you're right, CA and then BC inverse down here, for example, or AB, right? So here I believe I go just CA. So right now it's invertible. So I first go to A, BC inverse. And then this map, sorry. I believe I do this. See? Then this map, there's two maps. There's two maps that make this work, right? I can go to CA, BC inverse still, and I can still go to A, BC by just multiplying by C on the right, right? Does that make sense? So this was my P and my S. This is my J. This is my, are just defined to get me to these two things. So it's not the,
Thanks.
it's not the open immersion you expect. Okay. Okay, so now, unfortunately, I'm out of time. So I guess what I'll just say is that this doesn't work in general, but what you can do is that Q is a functor from graded rings to bigraded rings. So in the C star case. And even there's something you can do with GLV too, but I won't have time to mention it. So then you can derive this functor. So take a ring and replace it, a singular ring, and replace it by a simplicial, smooth simplicial ring, or smooth CDGA. Okay. Then apply Q. And all I'll say is that, so this is some kind of derived algebraic geometry perspective on this Q. All I'll say for now is that this always gives a fully faithful functor. In the smooth case, this reduces to the usual thing. If in partial results with Ballard and for complete intersections, singular complete intersections, this also gives an equivalence due to work of myself and Cheatham Barham. And so, for example, for the Mukai flock, and probably in forthcoming work, this also works for stratified Mukai flock. But that's in progress. So I'll stop there.
Right, any questions?
Can I ask a very naive question, David?
Mm-hmm.
So when you talk about sort of deriving a functor like this usually means, you know, taking cofibrant replacement for some model structure, or, you know, projective resolution in a simpler, more naive world. Are you suggesting that there is some sort of model structure where the sort of cofibrant guys are smooth on sort of?
I mean, since I didn't have time, but let's just talk about the cofibrant structure on CDGAs. Mm-hmm. I'm just talking about semi-free CDGAs. So there's a standard construction called the causal Tate construction. So if you have a singular ring, you can just replace it by a semi-free CDGA.
Cool. So by smooth you mean this? Cool.
Yeah.
Thank you.
I'll put smooth in quotations. So you can work over any smooth base ring, but yeah, I mean basically a free ring over a smooth base ring. Yeah, like a polynomial.
David,
CDGA.
David, and do you have a reference for this full faithfulness of the derived functor?
Yeah. So.
Mm-hmm.
So there's a paper by myself. I should list it alphabetically: Ballard, Deemer, and Favero. It's called, I think, Kernels from Compactifications. And there's another paper which is a bit easier because we work with CDGAs. of Cheatham-Barham and Favero. And we prove it in both contexts using, so in this one, this is simplicial rings. And it's quite technical. And this one is CDGAs. And I think it's actually very clean and straightforward. The newer reference. Okay. But most of what I talked about is in this first paper, or is in these two papers, I guess.
Okay, thanks.
Okay.
Other questions? Well, if not, let's thank David again. And we proceed tomorrow at 9.
Okay. Thank you, Ludmil.
Thank you.
Next time we'll get to play basketball.
Yeah. Let's hope if we're alive. Yeah.
Yeah.
Thanks for a very nice talk, David. I really enjoyed this.
Okay. Thank you, Tim.
Cheers.
Bye.